Welcome back, everybody. So, we've been talking about second law of thermodynamics. And specifically, we've talked about for a process from state 1 to 2. And so it looks like this. A change in entropy from state 1 to 2 is equal to the total amount of heat transfer divided by temperature to get from state 1 to 2, plus this other quantity called the entropy generated. And now what we know is every process is irreversible. Every process puts new entropy out somewhere. And that's what this entropy generated represents. This is either an increase in entropy within the system, or it could also be new entropy that's just out in the surroundings, somewhere out in the universe. But every time we have a process to get a system from state 1 to 2, if heat transfer occurs, that's going to cause an entropy change, or something irreversible occurs, and that causes an increase in entropy. And that's what the second law measures for us. Now, what we need is we need to be able to quantify that entropy change, right? How do we quantify this entropy change? Well, that's where we finished up last time. We talked about some different ways of quantifying an entropy change. And we said, well, one of those is table properties. Right? Works good for water and R134, table properties do. Another way we said was the second law itself. Right? The second law itself actually allows us to determine entropy change. If I can quantify these things on the right-hand side, then I can use that to quantify the left-hand side. And we said the third way, we talked about this, the last thing we talked about last time we were together was Gibbs Equation. Gibbs Equation is a way that allows us to determine a change in entropy. Okay, let's turn ink off to get to advanced. Looks fine. Alright, so that's, again, first way is table properties. Water and R134A, I just need to know two properties about my substance. Pressure and temperature normally works just fine. Pressure or temperature and specific volume works really good. Could be a pressure or temperature and the fact that it's saturated vapor, know the quality. All these are okay. Now, we said that is the first way, is using table properties. Doesn't work quite as well for ideal gases. We have another way we can try to quantify entropy change for ideal gases we'll talk about in a second. For water and R134, table properties work just fine. And if you've got property tables for other substances, you can do that for other substances as well. Some texts will have ammonia, propane, R410, refrigerant 410, so there are other substances we can find property tables. The second way we said is the second law itself. So again, if I can quantify these two terms, then I can use that to find an entropy change. And so there's a few ways that that can occur. We can talk about these here. I think we've mentioned these before, and that's okay. We said if it's adiabatic, then this integral of q over t, dq over t, again, if I just add up a whole bunch of zeros, I still get 0. If it's adiabatic, there's no heat transfer, so the sum of 0 is still 0. Maybe, though, we have what we call an isothermal situation, or we could approximate the temperature at which the heat transfer occurs at a reasonably constant average temperature. So what happens is if this 1 over t can come out of the integral, then I'm just integrating dq. Well, the integral of dq is just q, and so how we would normally write this, in a lot of texts, we'll just simply say, well, this is actually just q net in. So we add up all of the heat in, subtract all of the heat out, and everywhere heat transfer occurs, divide it by temperature. That's the reason for the summation. We're saying Take everywhere heat transfer occurs, divided by the temperature at which that heat transfer occurs, add the heat in, subtract the heat out, and that's what this quantity represents. We're saying here with the integral, with the partial derivative, we're saying go out and everywhere for the entire process from state 1 to 2, add up every little tiny slice of heat transfer divided by the temperature at which it occurs. So the integral is more general, but it is a bit overkill for an introductory thermal course like this. A lot of texts will just simply say sum Q over T. So add up all heat transfer divided by the temperature at which that heat transfer occurs. Max and min are normally dead giveaways that I'm dealing with a reversible situation where there's no entropy being generated. Now that's not always the case. Again, you really need to think about what is the purpose of the device, and is the problem statement telling me this is the best possible version of that device? Maximum output or minimum input are normally good ways we can say that. But again, what is the goal of this device? What does this device do? And has that problem statement told me enough information that I can assume that this is the best possible version that's reversible? So these are the three things that we would be able to do to the right-hand side of this equation to try to quantify the left. This guy is either 0 or it's Q over T, Q in over T, or Q net in over T. And this guy is either 0 or it's what we're solving for, or it's, in a rare situation, it could be a known quantity that somebody's measured and they're just giving us an actual value. Okay? And then the last thing we talked about, the third way we can determine a change in entropy, we said was Gibbs equation. We derived these last time. There's no reason to derive them again. But Gibbs equation, Gibbs free energy equation, sometimes it's called, allows us to approximate an entropy change for different substances. And so if I'm dealing with solids and liquids, that entropy change is approximately equal to the specific heat. Our text likes to use C sub P for solids and liquids. A lot of texts will just use C times the natural log of T2 over T1. And then for ideal gases, Gibbs equation can take a couple of forms. The change, these are little s's, right? These are little s's. These are energy per unit mass per temperature, right? A specific entropy, little s's. The specific entropy change, which is equal to the integral from T1 to T2 of C sub V dt over T, plus R ln, and this is ratio of specific volumes, little v's, little v2 over little v1. And what we normally do is we approximate this specific heat as constant at the average temperature. So this is C sub V average ln T2 over T1, because the integral of dt over T is the natural log, plus R ln, and again, specific volume ratio, little v2 over little v1. That's one way to find it. Another way you can find an entropy change is the integral from T1 to T2 of C sub P dt over T. And this one is minus R ln ratio of pressures, P2 over P1. And the same thing, we can do the same thing here that we did there. We can say this is approximately C sub P average ln T2 over T1 minus R ln P2 over P1. Now, which one do we use? Well, I don't know. Depends on what you have, right? In both cases, you need to be able to figure out the temperature change. If I've got a control volume, it's more likely I know the pressures at the inlet and outlet of the control volume. If I have a closed system, it's more likely I know the volume of the closed system. It's possible I know the pressure in either case, so I don't have to only use this for control volumes and only use this for closed systems. I'm just telling you it's likely those will normally be the situations you deal with. If I've got a closed system that's constant volume, Notice what happens if I take the natural log of 1. If you don't remember that, pause the video and on your calculator take the natural log of 1. So notice what happens if I've got a closed system that's rigid or constant volume. This guy does something really cool. Okay. Okay, so that's quickly what we did last time. Now, let's continue on then, shall we? So I've got a couple of examples we can work through today. This one will work through one, and then I've got another example work through a couple of different ways. But this one says that I've got an insulated tank, and we've put a hot piece of copper into the tank. So the copper is going to start out at 80 degrees C. That's pretty warm. And the water is going to start out at 25 degrees C. We want to know the final temperature, and we want to know the entropy change, total entropy change. Now, they told us I've got 50 kilograms of copper dropped into 120 liters of water. Okay, so let's collect our givens. Let's just set this up like we would any other normal problem. The only difference is now we know some stuff about the second one. Okay, so we set this up like any other problem. We say, all right, well, what do we know? We have been given the mass of the copper is 50 kilograms. They didn't give me the mass of the water, but they did give me the volume of the water is 120 liters. So I think we can use that to figure out the volume. I'm sorry, the mass. They've told me that there's an initial temperature of the copper. The copper is pretty warm. It's coming in at about 80 degrees C. We're putting it in this water to cool down, T1 of the water being 25 degrees C. They want us to find the final temperature, and they want us to find the entropy change. And again, I've got this tank, copper, a big chunk of copper, and I've got water surrounding it, and this tank is insulated. Okay. Well, we find the temperature. Well, what all's going on here, and what are some good ways we might try to find the temperature? What are some tools we might have? And you say, well, this is a thermodynamics course. We do have the laws of thermo. Do those help us somehow? Well, what does the first law tell us? The first law tells us, of course, energy is conserved. And maybe that is helpful. So the first law always says in minus out equals change. So we add the in, subtract the out, and that equals the change. What crosses the boundary here? Yeah, I don't see anything. Nothing crosses the boundary because they told us it's insulated, by the way. Meaning there's no heat transfer. So there's nothing crossing the boundary, so that's going to equal the change. I'm just going to write big U, big delta U total. Now the total internal energy change, there's going to be two things changing internal energy. I've got copper, and I've got water. Okay. I don't know if that helps us yet. We'll see. I do know if I start saying, all right, well, what do I know? Remember, for solids and liquids, these U values are going to be functions of temperature. So if I know these U values, I know the temperature. If I can describe the change, that might get me to this unknown temperature that I'm looking for here. Okay, well, so let's continue working this down. We may get down this rabbit hole and not get to a solution, but it's always worth a try. I'm going to have to pick up there on the next video. So, you can hear it pop.